So we can use this idea of isoelectronic, and we will learn what we call the octet rule. There's two ways to state the octet rule. The first one we're ready for right now, and it says that the atoms react to become isoelectronic with the nearest noble gas. It doesn't have to be the last one they passed. It's whichever one's the closest. Sometimes we'll go forward, sometimes we'll go backwards. So in other words, the magnesium here, it could have gone forward to argon. It would have had to move forward 6 boxes. Or the magnesium could go backwards 2 boxes, which seems easier. Which is easier, going forward 6 or going back 2? Going back 2. And so the magnesium, that's what it's going to do. It's going to react to get to neon. That means it'll have to go back 2 boxes. It'll be a +2. So if I look at this and I say, here's iodine, which is closest? Krypton at 36 or xenon at 54? Xenon at 54, so it's going to move forward 1 box. If it moves forward, it'll have a -1 charge. Now, the other statement of the octet rule has us realize that these noble gases have 8 valence electrons, because they were S2 and then P6. They had 8 on the outside. They're not only trying to get to the nearest noble gas, they're trying to get to 8. So they're reacting so that they try to get to 8 valence electrons. But then when they turn around and they put in parentheses 2 for helium. Because helium doesn't have 8 valence electrons because it doesn't have any P's. It's only got 2. That first layer only holds 2. What they're really doing is they're saying they want the outside layer full. They want it to have 8. Now this one's a little sneaky though, because if you get up to 8, that's great. But if you go down to 0, it's the same as getting up to 8. So I'm going to come back to that magnesium, and we'll look at magnesium here. It has 1, 2 in the first layer. Then it has 8 in the next layer. And then this next layer, the third layer, it says it has 2 electrons. 1s2, 2s2, 2p6, 3s2. That's what all that's telling you. First layer has 2. The second layer, that's both of those 2, is these 8. And the third layer only has 2. So it can react to try and gain. I'll try to do it so they can see. It can either gain 1, 2, 3, 4, 5, 6 more to get to 8, or it can do what? It can go down. And so if it goes down and it loses both of those, then this outside layer is empty. If it's empty, it's no longer the outside layer. The new outside layer is that one. And it's already full. This is old cooking. This is a guy's cooking trick. So learn this real quick. I always tell my guys that I give them advice. I say, you need to learn to cook a couple of meals. You gotta learn to cook some kind of meat outside, or if you're vegetarian, some kind of thing on over fire is the way I like to put it. I think it's really helpful to be able to cook breakfast. And then I like to be able to cook, I like making omelets. That's my go-to breakfast when I was a young man. And make an omelet, and you go to the fridge and you pull out an onion. You only got one, but that outside layer is kind of nasty looking. It's been sitting in that fridge since the last time you had a date. Right? What's a guy gonna do? Peel it off and use the next layer down. That's exactly right. And that's what we're doing here. We're getting rid of the unfull one that's natural and expose the next one down. Like I say, speaking of dates, there goes my wife. So that's the key to this octet rule. We're trying to get where? Where's our magic elements that we're trying to get right? Which ones have 8? They have the S2 and the P6.
The P6.
Which one's it? What else? What's the name of that? S2, P6. Over here. What were those called? Noble gases. That's our magic one. So everything's trying to get to the noble gases. The noble gases happen to have 8, except for helium, which has 2. This 8 helps you remember that this is called the octet rule. How many arms does an octopus have? 8. So everything's trying to get to 8. So that's where this name came from. Everything's going to react to get to the noble gases. But this only works, our octet rule only works for the representative elements. Uh-oh. We got to figure out where the representative elements are. So I'm going to go right back. Representative elements. On this old periodic table that was in our book here, or at least in the old book, there was these things that had the A. They had some kind of Roman numeral in front of them, and they had A. It's even labeled on this one. How nice. It says representative elements, and it's got these over here labeled. Oh, you can bet on that second test, they won't have that on there anymore.
They have 2 labels.
It's got these here and those up there. So it's groups 1A, 2A, and then 3 through 8A. But when I look on the periodic table up here on the wall, it doesn't use those A numbers. Because its A numbers only work on the American periodic table. It won't work on the Russian periodic table, and it won't work on the new international one. So let's get the other names for these. Well, these are groups 1, 2, and 13 through 18. 1, 2, and 13 through 18. Those are our representative elements. You also hear me sometimes call them main group elements, because we used to call them that. They were the ones the rules worked for. 1, 2, and 13 through 18.
And 1 and 2 came from, of course, 1 and 2.
1, 2, and then these
13 and
13 through 18.
Okay.
In other words, since we've done electron configurations, we've got the S and the P blocks. When we're dealing with the D's and the F's, in other words, the transition elements, the octet rule doesn't really work very well. They do some craziness. S and the P. Now, these A names were handy because they could tell me the valence electrons. So I didn't always have to go and do my electron configuration. We can get that from the electron configuration. Remember when we did fluorine, it was 1s2, 2s2, 2p5. And I said it had 7 because we want the biggest numbers there. We could also have done the fact that it is in 7a. So it had 7 valence electrons. You just take the Roman numeral in front of the A. And that's telling me the valence electron. So everything in this column has 7 valence electrons. And everything in this column 4A would have how many valence electrons? If it's 4A, it's got 4 valence electrons. Just take it right off of that. But we need to be able to do it when we are looking at this and we don't have those A numbers. So let's figure that out. Let's see. Group 1 has 1 valence electron. Group 2 has 2. We just take our number up there. And then group 13 has 3 valence electrons. What we did is we did 13 minus 10. That's how we get our 3. What 10 am I subtracting out? I'm subtracting out these 10 that are in the D's down here. Because they don't count. Remember, they're one layer below. Now, this idea of subtracting 10 is great. When I do fluorine, for instance, it was 17. And so that would be 7 valence electrons. But I don't even think about the subtracting 10. I come over here, I go, hey, it's in 17. I'm going to ignore that 1.